There is something wrong with the universe, and nobody really knows what it means at the moment. The James Webb Telescope has certainly discovered galaxies that theoretically existed before the Big Bang. This calls into question the Big Bang theory and our entire cosmology to date. Science is faced with a seemingly unsolvable problem. Although researchers such as the Swiss Fritz Zwicky already knew of alternative explanations for our universe 100 years ago, and it's precisely these that are now becoming topical again. Hardly any school children today know the name Fritz Zwicky, but we do know names such as Albert Einstein, George Lemaitre, and Edwin Hubble. These are the researchers whose theories laid the foundation of our cosmology for almost 100 years. Albert Einstein described space-time, Lemaitre came up with the Big Bang, and Hubble observed the apparent expansion of the universe. But now all these theories are being put to the test, and the new superstar among telescopes is responsible for this, the James Webb Space Telescope. This marvel of technology has given us so many fascinating images of a previously unknown universe that we now know. The old theories can only be wrong, or at least incomplete. Fritz Zwicky was a contemporary of these great researchers. The Swiss physicist, who also studied the movement of galaxies and the dynamics of the cosmos, came up with a theory that is once again topical and the subject of heated debate today. The idea of tired light is very simple. Zwicky postulated that light is not constant, as Einstein claimed, but that it undergoes a physical change during its journey through time and space, which he called fatigue. Einstein said that nothing travels faster than light, and that the speed of light is always constant and does not behave relatively like all other known forces in the universe. It seems logical that researchers have long used light and the speed of light as the great benchmarks for exploring the universe and determining such important values as distances and the rate of expansion. Before we look at the possible flaws in these theories, let's take a look at some of the fascinating galaxies discovered by the Webb telescope. Galaxies that are absolutely impossible. With its ultrafine sensors, the Webb telescope looks further back in time than any other telescope before it. Thanks to red light spectrography, Webb can detect light that is very small and very shifted into the red. The first deep image of the universe showed galaxies that existed in an epoch 13.6 billion years ago. The amazing thing was that no galaxies actually existed at that time. It all started with the astonishing discovery by Harvard student Rohan Naidu. He and his team announced the discovery of Glass-Z13, a galaxy that demonstrably existed around 200 million years after the assumed Big Bang. Its age already suggested at the beginning of the Webb era that galaxies could have evolved faster and earlier than previously assumed. However, some researchers did not believe this at first. GN-Z11 followed, and with an estimated age of 13.4 billion years, this galaxy once again provided overwhelming proof that the old theories are no longer tenable. GN-Z11 is one of the most distant known objects in the universe and was originally discovered by Hubble, the old space telescope. The discovery was only confirmed by the new Webb telescope. GN-Z11 offers insights into early star formation and galaxy formation in the young universe thanks to Webb's stunningly accurate spectrometer analyses. It is currently clear that stars and finished galaxies existed much earlier than previously known. Sears-93316 was discovered by the Cosmic Evolution Early Release Science Survey. This galaxy was originally estimated to be an incredible 13.8 billion years old, which has sparked enthusiasm among some researchers and brought others to the barricades. The other galaxies still allowed for ideas of a much faster evolution of matter. This was, so to speak, the loophole for all the researchers who were only too happy to hold on to the Big Bang. A galaxy that is just as old as the Big Bang blows up this picture and makes new approaches such as the eternal universe or Zwicky's theory of tired light more likely. The age of Sears-93316 is still the subject of heated debate, with the discoverers constantly presenting new evidence for the authenticity of the find and critics attempting to refute this evidence. HD1 is another unusual galaxy and has an estimated age of 13.5 billion years. It is one of the most luminous galaxies among the very old galaxies discovered so far, indicating an unusually high rate of star formation. These are the facts that scientists are looking for, because HD1 could help us to significantly deepen our understanding of the conditions and processes in the universe during this epoch. Let's take another look at MAX 0647-JD. It's not one of the more unknown newly discovered galaxies, but it still has some interesting features. MAX 0647-JD was discovered by gravitational lensing with the Hubble Space Telescope and then further studied with the Webb telescope. With an estimated age of 13.3 billion years, MAX 0647-JD is not one of the oldest galaxies, but strangely one of the most evolved. It only existed 500 million years after the Big Bang, but shows such a high degree of order and size that this galaxy should actually be several billion years old. This means that the time of formation of this galaxy would also have been before the Big Bang, which cannot be the case. These galaxies are only 5 of 15 confirmed impossible galaxies, and there are more and more. Tired light. Zwicky already knew it 100 years ago. Imagine the most crucial component that scientists have used to study the universe has been misunderstood until now. Light is not constant, but becomes tired over time. Minimal differences are enough to change distances of several million light years in such a way that our measurements are completely wrong. Another possibility within this theory is that light physically behaved completely differently 13 billion years ago. You have to imagine that the light that now hits the observation mirrors of the Webb telescope was emitted 13 billion years ago, or more, by stars that no longer exist. Of course, the Earth did not exist at that time, not even our Sun, and it's very likely that only a small precursor of our galaxy existed. These particles of light therefore traveled incredibly far and for an incredibly long time. As the light traveled, space also expanded. If the idea of the expansion of the universe is really true, this expansion could have stretched the light, but we don't know that for sure. We have no way of measuring or investigating the original light. We can only deal with the light that has undergone this extremely long journey. We could also never travel back to the time when the light was created. Despite these hurdles, these faint light signals are actually miraculous. The mysteries of time and space and the journey of light allow us today to study the universe as it was 13.5 billion years ago. This is fantastic. Interpreting the signals is really a bit of a guessing game. Researchers have to take all the fixed, known quantities, then derive constants, similarities, and a meaning. This is how our theories and explanations are created. In addition to light, there are several other quantities that researchers use to measure and describe space. These are certain phenomena that always behave in the same or coherent way. If it now turns out that this was precisely the mistake, we really are facing a complete reorientation of science. Rajendra Gupta is a Canadian researcher who, in 2023, put forward a theory that shows that a small modification of these cosmic constants quickly leads to a much older universe. But not only the age of the cosmos would then change, variables relating to expansion and origin could also be completely different. Gupta presented a coherent calculation according to which the universe could be 26.7 billion years old. However, he also showed that a further small adjustment would lead to an age of 40 billion years. This would explain in a simple way why we see masses of galaxies in Webb's images that suggest a much older universe. Gupta also considers Zwicky's ideas and shows that the picture of our universe turns 180 degrees when just this one small component of tired light is taken into account. Science can go no further. It is fascinating to observe how the world of science reacts to the new circumstances. One person who is excited about the new findings is US astronomer and astrophysicist Michio Kaku. Kaku is regarded as an exceptional researcher who has written many books to bring the mystery of the universe closer to ordinary people. He enthusiastically explained that the Webb telescope completely reshuffles the cards in science, and Kaku welcomes the changes. He knew for a long time that something couldn't be right. Kaku, in addition to his passion for the visible universe, is a big proponent of quantum physics. Quantum physics and classical physics still don't really go hand in hand, which proves once again that we must have a flaw in the system. Other researchers, such as the project leader of the Webb telescope, John Mather, are sticking to the old theories. Mather told the press that he firmly believes that the Big Bang 13.8 billion years ago was correct, and that matter and therefore galaxies were formed faster than previously assumed. A third scientific genius whose name is currently being discussed a lot in the press is Sir Roger Penrose. A few years ago, the scientist from Great Britain postulated a cyclical universe in which there is a kind of basic matrix that transports the idea of matter from an old universe into a new one. According to this, all information is stored when an old universe dies, and in this way, matter could be quasi-turbo recycled in a new universe, which could have led to a faster formation of stars and galaxies. Penrose's model also predicts that black holes play a crucial role in these cycles. In his model, they are pretty much the last objects or physical entities left at the end of a universe. After they have sucked all the matter into themselves, they evaporate or collapse at lightning speed. This moment of collapse is basically the birth idea of the new universe. Surprisingly, several research groups from the USA proved in 2023 that our universe could theoretically have been created in a black hole. How old is the universe really? Did you believe that our universe is 13.8 billion years old and was created from a huge explosion? Although the theories were consistent, there were always doubts. If we look closely, we have recently found more and more evidence of inconsistencies in the expansion, misinterpretations of distances, and corrections to the age of the universe. James Webb is now only ending a discussion that began a long time ago. Thanks to ever-improving technologies, we have apparently been able to understand the age of the universe more and more reliably. But those who have paid close attention have also found evidence that scientists are guessing more than they know. The age of the universe was corrected 3 times until we arrived at the current 13.8 billion years, and Webb now shows us that this is also wrong. A central topic in the discussion about the true age of the universe and the distance of galaxies has always been the phenomenon of redshift. Redshift refers to the elongation of light waves to longer, reddish values. The values determined were usually interpreted as a measure of the speed at which a galaxy is moving away from us. The greater the redshift, the faster the movement, and the further away the galaxy is. This observation has long been one of the key pillars of the expanding universe theory. But now this redshift of all things is being put to the test. It may have been misunderstood from the very beginning. We do not know how dust, gas, and other interstellar matter can influence the light on its way to us, resulting in color values that we may have misinterpreted. The Swiss Fritz Zwicky came up with another exciting idea that paints a completely different picture of red light. Around 100 years ago, he postulated that light undergoes a change as it travels through space because it undergoes minimal fatigue. Zwicky's theory states more precisely that the redshift is not caused by the expansion of the universe, but by the interaction of light with matter or radiation fields in space, which causes the light to lose energy and become redshifted. In plain language, this means that the source and the observer are not moving away from each other, which would mean that the idea of expansion is gone. What would this mean in practical terms? The question can be answered in several interesting ways. Firstly, it would mean that space does not expand from a starting point. This would also mean that the idea of the Big Bang would be gone, and with it the idea of how the universe will end one day. Here we have so far the Big Rip, which is caused by overexpansion because the universe has expanded too far. The Big Freeze says that the expansion will have robbed the universe of all its power at some point, causing it to freeze. And the Big Crunch tells us that the universe will break up at some point. Expansion is also supposed to be to blame here. But what if it doesn't exist now? Then we might be living in an infinite universe after all, in a bubble universe or in a 12-dimensional universe, of which we can only describe a very small part with our current physics. Can we find out the true age of the universe? Of course, this raises the exciting question of whether we will ever be able to find out the true age of the universe or its size. At the moment, we don't know whether we will succeed. It's possible that new spaces and surprises are constantly opening up, and that we will never come to a beginning and an end with our research. Just think, 500 or 600 years ago, people still thought the Earth was a disk. Then, even astronomers thought the Sun revolved around the Earth. And today we look an incredible 13 billion light-years into a cosmos that never ends and surprises us again and again with completely new things. Anyone looking for solid explanations and evidence will be disappointed, but anyone who loves new things and mysteries will get plenty of new input from James Webb. Rajendra Gupta, a Canadian researcher, put forward a theory in the summer of 2023 according to which the universe could be 26.7 billion years old or even older. His calculations are based on new findings, Zwicky's idea of tired light, and a variation of the cosmic constants. The design has already been tested and is consistent. However, this does not mean that Gupta has discovered the truth. We will only find it through observation. Imagine James Webb is still showing us older galaxies and even more impossible things. We may soon look back 14 billion years and see a universe that looked exactly like it does today. This would mean that the Big Bang was even further back or that it never happened. What is certain is that all new findings from real observations take us a step further. For almost 100 years, observations such as black holes and galaxy dynamics have largely confirmed the old physics, but now everything is different and a time of upheaval has begun. Our physics is stuck on several levels, and this could be the solution. Microcosm and macrocosm. Something is wrong here. What hardly anyone knows is that physics is currently reaching the limits of the impossible at almost all dimensions. Astrophysics has reached its limits with these galaxies and very old and gigantic black holes. In the world of the smallest particles, researchers know no further. At the very latest, the small particles become so unpredictable beyond Heisenberg's uncertainty limit that we can no longer grasp them. Researchers working on the current structure of the large-scale universe are also at a loss. The more we look at it, the less the patterns and structures fit with the ideas of the Big Bang and expansion. But what does this all mean? We are at an exciting threshold where completely new things will be revealed in the microcosm, in the macrocosm, and at the beginning of our universe. It has long been known that the physics of the largest phenomena cannot be reconciled mathematically and empirically with the findings of quantum physics. But quanta are also the building blocks of stars, planets, and galaxies. If these two disciplines do not fit together, it's not because there is something wrong with our universe. The researchers simply do not know where the connections and errors are. The current crisis can be a huge opportunity for science, but some gray eminences of astrophysics will certainly have to step down now. Will the researchers come to a consensus? It's crazy. Scientists are arguing about being right and whether they can stick to theories that have never been concretely proven by observations. No one has ever really seen the Big Bang or the universe expand. James Webb is now showing us a bit more of the truth, and it's actually unbelievable that scientists are protesting and continuing to defend their obviously false theories. The scenario is somewhat reminiscent of the Middle Ages when Galileo Galilei ended up in church prison because he had observed that the Earth revolved around the sun. But there is also good news. Young researchers such as Harvard doctoral student Rohan Naidu are rejoicing at the new facts. There is a community of young or even older and open-minded astronomers and cosmologists for whom the old explanations have long been inadequate. Naidu used his algorithm to discover some of the oldest galaxies on James Webb's depth image. As soon as the depth image had been released by NASA, Naidu fed his computer with the data, and shortly afterwards the sensation was perfect. The galaxy Glass C13 came to an age of 13.6 billion years using the old calculations for the red light shift. This means that it already existed 200 million years after the supposed Big Bang. And since this galaxy must be at least several hundred million, if not 2 to 3 billion years old, something can't be right here. The discovery was the prelude to the crisis. The redshift was doubted, James Webb's technique was scrutinized, Naidu's results were questioned. but the age of the galaxy was confirmed several times over. The James Webb Space Telescope brings down the house of cards. Michio Kaku is the most popular astronomer in the USA, and he was beaming at the findings. Kaku is one of the few people who seriously try to bring quantum physics and astrophysics together, and he sums it up. James Webb is now finally bringing down the inconsistent house of cards of astrophysics. Nobody had expected this shock, because many of the old scientists were firmly expecting James Webb to confirm their theories. So will science find a consensus or not? It must, because the universe does not lie. Currently, many of the new findings and studies are going through peer review processes where scientists submit their research findings for evaluation by other experts in the same field. Possible errors are identified here, and reviews often lead directly to ingenious further developments and new ideas. We can be sure that research will be more cautious in the future about what is presented to us as the truth. The heresy of the Big Bang 13.8 billion years ago is embarrassing enough. Sir Roger Penrose, the British astrophysicist and Nobel Prize winner, warned in view of the new situation that we must go back to the point where we have reliable data and observations. Ultimately, this means that all theories based on dark matter must go, because we don't know whether it really exists. This means that the entire previous cosmology will collapse and the universe will be completely reassessed. Can Euclid prove dark matter after all? Let's take a moment to look at another brand new but somewhat quieter astronomy star in the night sky. Euclid has been positioned in space since 2023 and has a special mission. Euclid is to produce the best map of the known universe we have ever had. James Webb is designed to focus specifically on individual points, galaxies, planets, or far into the distance. Euclid's mirrors, on the other hand, work in such a way that the telescope captures broad areas and maps the entire cosmos visible from Earth. This new data should prove, among other things, the existence of dark matter and the dynamics of the equally hypothetical dark energy, or not. If researchers find no evidence for their existence in Euclid's data, it will once again be a close call for all those scientists who firmly believed in the existence of these two variables.
Sabir Sarkar is a professor of astrology and cosmology at the famous University of Oxford. The scientist is absolutely right when he says that these days we cannot possibly hold on to knowledge based on the knowledge and technology of the 1920s. The scientists of that time did a great job, and they provided a coherent picture of cosmology for a long time. But this work has now been overtaken by facts. Current observations show that the universe is not the same everywhere, and this calls into question one of the fundamental pillars of cosmology, the homogeneity of the universe. This phenomenon and other pressing questions about the current crisis in cosmology were discussed by a group of the best international experts. The Venerable Royal Society in London had invited a select group of the best astronomers and cosmologists of our time to an illustrious gathering. These scientists are now warning a new age is coming. The old theories and statements of almost 100 years ago are no longer valid. It is very likely that a certain portion of our observational data is correct, but we have very probably fundamentally misinterpreted these observations for a long time. Something is wrong. The universe can't possibly look like this. Have you ever thought about the fact that our universe should still be basically the same as it was shortly after the Big Bang? It sounds strange, but it is true. Astronomers like to use the comparison with a balloon to explain this idea vividly. If you blow it up, the dots and patterns on the surface move on and on. They change their structures, shapes, and positions, but the basic patterns remain the same. In the same way, scientists have calculated our existing universe back to a starting point and have used the cosmic microwave background radiation to deduce the basic structures of the universe. Classic cosmology, which was based on these and other ideas such as uniform expansion, subsequently assumed that the universe is homogeneous and isotropic on large scales. This means that it should look the same in all directions and show an even distribution of matter and energy. This assumption is inextricably linked to many other fundamental theories such as the Big Bang and expansion. But there is a problem. According to this theory, if you look at the universe on the largest scales achievable, there should be no noticeable structures or anomalies. All we should see is a largely uniform distribution of galaxies, similar to an evenly sprinkled cake. But the reality is different. The James Webb Space Telescope is a milestone in modern astronomy, and it has provided images and data that challenge these basic assumptions since its launch in the summer of 2022. The JWST has discovered structures in the early universe that are so massive and expansive that they defy the notion of a uniform distribution. It is as if there are lumps of icing or completely empty spots on our cake that should not be there. These structures include large clusters of galaxies that existed very early in the universe and unusual distributions of quasars. These observations and other anomalies show that the universe is anything but homogeneous on these large scales. The unexpected destiny in the distribution of quasars, for example, is in no way consistent with the old models of homogeneity. Quasars are extremely luminous cores of distant galaxies. One side of the universe shows a density of these quasars that is about 0.5% higher than the other. This asymmetry in the universe is comparable to a cake icing that is so overloaded on one side that the balance of the cake would be disturbed. What do the Great Ring and the Giant Arc reveal? Two structures that are considered impossible simply because they are far too large are the Large Ring and the Giant Arc. These structures were discovered by a young astronomer named Alexia Lopez. Together with her team, the US-American researched large-scale structures consisting of galaxies and galaxy clusters. These extend over scales which, according to standard theory, should be smooth and featherless. But they are not. The Giant Ring is a gigantic ring structure formed by a group of 9 gamma-ray bursts that are roughly equidistant from Earth. This structure is peculiar because, with a diameter of about 5.6 billion light-years, it is one of the largest known structures in the observable universe. Its sheer size is the problem for the standard model of cosmology, as this prescribes that on scales larger than about 1.2 billion light-years, the distribution of matter in the universe should be uniform. But the Great Ring is not uniform. The Great Arc is another structure that is too large and thus brings irregularities to our cake icing. The arc consists of an almost uniformly aligned group of galaxies that spans about a tenth of the entire known sky. This structure is thus so massive that it calls into question the cosmological principle that the universe should have no favored directions or regions of higher density on large scales. Researchers have been amazed at new anomalies and the facts that simply throw old theories overboard, and not just since the beginning of the JWST. We have known about irregularities for a long time, and even Hubble, the old space telescope, regularly delivered data that was not quite compatible with standard cosmology. You've probably heard the saying, exceptions prove the rule, and this also applies to a certain extent in science. In plain language, this means that certain outliers do not immediately call our theories into question. However, if the outliers occur more frequently and thus become a rule in their own right, or if the outliers even gain the upper hand, then something may no longer be right. This is precisely the case in cosmology. The Big Ring and the Giant Arc also contradict the assumption that dark matter and dark energy, which together are supposed to make up around 95% of the contents of the universe, are evenly distributed. The problem is that neither dark matter nor dark energy are proven facts, and we can only deduce them, not see or measure them. Both are important factors in the expansion of the universe and the dynamics of galaxies in the universe. It is possible that these two are complemented by other forces in gigantic cosmic rounds that we do not yet know. Now it's out. Hubble was wrong. Quote from Adam Rees, Nobel Prize winner and astrophysicist. Our previous picture of the universe is wrong. These are exciting times. We are at a turning point, the likes of which natural science has not seen for a long time. Around 100 years ago, great minds such as Albert Einstein were researching the forces and rules in a universe that was becoming even larger and even more unmanageable. Edwin Hubble discovered the first galaxies outside our Milky Way and realized that distant galaxies were moving away from us. This gave him the idea of the expansion of the universe, and he came to the conclusion that this expansion must start from a single point. The Belgian clergyman and researcher Georges Lemaitre finally formulated the Big Bang Theory from this idea, and since then, the basic model of cosmology has not changed much. Only now are there massive changes again. Nobel Prize winner Adam Rees saw these changes coming. Through his research on the Hubble effect, he was certain that our previous science must have overlooked something important about the true nature of the universe. The Hubble effect comes about because measurements of the rate of expansion of the universe show different results depending on which quantities are used as standard candles. Sometimes scientists measure using the cosmic background radiation, and sometimes they use a special class of stars, the Cepheids, as a standard. Both results should have been the same in the homogeneous universe, but this has not been confirmed. When the telescope named after Edwin Hubble confirmed these measurements for the first time, scientists were still able to assume a measurement error to some extent. However, the JWST has now confirmed the discrepancies, and the discrepancies in the rate of expansion have become a fact that scientists must now face up to. If the universe does indeed exhibit large-scale inhomogeneities, this could fundamentally change our understanding of how and why the universe expands, how galaxies form, and how structures are created in the universe. Many researchers currently assume that Einstein, Hubble, and other pioneers of 20th century astrophysics correctly identified part of how the universe works, but it was only part of the truth. DESI. Dark energy may be intelligent. The news is staggering. There is evidence that our universe really could have something like an intelligence. This would make it kind of a living being. This idea sounds far-fetched at first, but it is based on current cosmological findings. Until now, it was assumed that dark energy, as a cosmological constant, is responsible for the accelerated expansion of the universe and is the same everywhere. As a constant, this force would be the same everywhere. However, the variations in the expansion rate revealed by different measurement methods and the latest observations from the JWST show that dark energy is not as constant as once assumed. Recent data from the Dark Energy Spectroscopic Instrument, or DESI for short, indicate that the properties of dark energy have changed over time. This is interesting because it could mean that dark energy has some kind of intelligence, or at least variable dynamics, which we in science previously thought impossible. DESI is a project that has done one of the largest 3D mappings of the universe, and that data showed the surprising new data. If dark energy has evolved over time and is not constant, as Einstein assumed, this could explain why different measurements give different values for the expansion rate of the universe.
The Hubble Constant. If we turn back the wheel of time by about 100 years, we'll land in an era when a tremendous tremor swept through the ranks of space explorers. Together with a colleague, the American astronomer Edwin Hubble had devoted himself in the late 1920s to the arduous task of analyzing the light of dozens of galaxies at the Mount Wilson Observatory in California. At the end of this series of investigations was a groundbreaking conclusion. As the Belgian Georges Lemaitre had postulated several years earlier, the light from the remote collections of stars was indeed redshifted. By finding that virtually all galaxies drift away from us and that their velocity increases with distance, Hubble showed that the universe is a construct that has always been expanding. This fact, which today belongs to the astronomical general knowledge, amounted to a scientific revolution at the time. A conception that a certain Albert Einstein initially categorically rejected. In order to maintain the image of a rigid, unchanging cosmos, the genius had even inserted the cosmological constant into his equations, a decision that Einstein later described as the, quote, greatest folly of his life. But how can we actually find out at what speed our universe is expanding in detail? Well, in order to package this process in suitable numbers, the experts make use of the so-called Hubble Constant. As one of the fundamental quantities of cosmology, this describes the current expansion rate of the cosmos. However, since strictly speaking, it's not a constant, it is sometimes replaced by the term Hubble parameter. To determine the exact value of this parameter, researchers systematically analyze the distance and apparent velocity of astronomical objects. However, in order to determine the expansion rate of the universe, distant objects in particular must be observed, an extremely demanding task that also leaves a large margin for uncertainty. From the past measurements of ESA's Planck satellite, it became clear that the exact value of the Hubble constant settles at about 67.15 kilometers per second per megaparsec. A brief classification: the length unit megaparsec corresponds to approximately 3.3 million light-years. So that means a galaxy 3.3 million light-years away is moving from us at a rate of 67.15 kilometers per second. A collection of stars that is 10 times further away from us is therefore also traveling 10 times as fast. The problem? Recent measurements showed that these values simply do not coincide with reality. But what is the background of this unexpected deviation? Does this mean that we must throw our usual conception over the cosmos completely out the window? An upheaval. But first things first, why is it actually so important for experts to know the exact value of the Hubble constant? Well, on the one hand, the expansion rate can give us a preview of the further development and fate of the cosmos. On the other hand, it also gives us a mathematical insight into the past. If we look at the expansion of the universe backwards, we can calculate our way back to the birth of the universe. As a consequence, the Hubble constant can provide us with fundamental information about the age, the expansion, and the composition of the cosmos, if it has been determined correctly, of course. The observations in our cosmic environment revealed a strange contradiction in this respect. Thus, the investigations showed that the value of the Hubble constant in our proximity does not amount to 67.15, but up to 74 kilometers per second per megaparsec. Still, other measurements, using the brightness of supernovae or variable stars to determine the distance, yielded values between 72 and 74 kilometers per second per megaparsec. Before the world of astronomical research was enriched by a mystery, Adam Rees and his team at the Space Telescope Science Institute in Baltimore had taken a close look at about 70 Cepheids. These are stars whose brightness fluctuates more or less regularly. Based on the stellar flickering, scientists were able to determine the distance of the celestial bodies and, against this background, also the expansion rate of the universe. If one follows the calculations of the experts, this lies with 74.03 kilometers per second per megaparsec, with which it exceeds all values determined before. The fundamental question that astronomers have been racking their brains over ever since is therefore, why do we get different values for a fundamental parameter of cosmology simply because we measure differently? In theory, the result should always be the same. To all appearances, something is wrong. However, this should not apply to the actual universe, because casually said, the cosmos should not care much about what the scientists calculate in their earthly research facilities. No, the question is rather whether the model with which we describe the expansion of the universe so far is really the correct one. A profound insight. If the expansion of the universe is not homogeneous, that is, if some parts of the universe are moving away from us faster than other objects located at the same distance, then we would be faced with an asymmetry, a fact that would also mean that the cosmos, in its entirety, cannot be calculated back to a uniform starting point. Is it conceivable then that the roots of this mystery lie dormant in the Big Bang itself? Did the common emergence of matter, space, and time from a preceding singularity in truth not proceed symmetrically? Were the asymmetries we can see today in the distribution of galaxies and structures created by the force of gravity and other physical forces? Or was this pattern already laid in their cosmic cradle? But if the idea of the asymmetrical emergence actually coincides with reality, Wouldn't it then be conceivable that the starting point of the universe was not 13.8 billion years before our time at all, but earlier or later? A question which inevitably goes along with the variance of the recorded measuring data. Now, one could think that it would not be further significant whether the cosmos is 15 or 12 billion years old at the end. Unfortunately, it's not quite that simple. Since the Hubble Constant, or the expansion of the universe, also affects many other aspects of space research, we would have to question and rethink everything that touches on this subject area. The search for answers. The aforementioned study author, Adam Rees, stated about his much-publicized discovery that the discrepancy in the Hubble Constant could become one of the most exciting developments in cosmology in decades. Since this fact has been investigated and confirmed several times in the meantime, it's considered impossible that simple measurement errors underlie the collected data. But then, what are the ways and means to explain the puzzling deviation? One approach is based on the influence of the ominous dark energy. This hypothetical form of energy, which has not yet been experimentally proven, was postulated in the late 1990s to explain the accelerated expansion of the universe. In very simplified terms, dark energy counteracts gravity, driving individual celestial bodies and structures ever more forcefully apart. Even more exciting, however, is an attempt to explain the reasons for the variance of the measured data not at all in our cosmos. As the published study shows, it's theoretically possible that the deviations of the Hubble Constant are created by a parallel universe. In detail, this strange world would interact with ours, however, only on the basis of gravity. This assumption, which seems to be difficult to imagine at first, has already been discussed seriously in the ranks of researchers for a long time. If one follows the theory of chaotic inflation, which the Russian cosmologist Andrei Lind brought into the field in 1986, then the majority of the universe continues to expand eternally inflationary. This process would come to a standstill only in some bubble-shaped partial areas, in which, then, the individual sub-universes form. These would contain, again, completely different values of the nature constants and consequently, also individual physical laws. Whether the recorded measuring data are really based on the influence of an invisible mirror world can be neither confirmed nor denied at present. In order to confirm this hypothesis, it is indispensable to track down further evidence for the existence of such a parallel universe. Before then, we look spellbound on those realizations which will attain the researchers in this connection in the future. No stone has been left unturned since the JWST showed us images of galaxies that are so old and so perfect that they shouldn't even exist. This was the beginning of a drama in modern science that continues to the present day. More and more images show even crazier phenomena and impossibilities. Nothing in the young universe is the way scientists thought it would be. And now it's also clear that the entire universe is not the way our scientists thought it would be. Until now, researchers have assumed that the universe is homogeneous, meaning that its large structures are largely uniform in shape. But now, there are dozens of indications that the universe is in fact inhomogeneous, and this calls into question some of the basic assumptions about the nature of the cosmos. The idea of a homogeneous universe goes back to the cosmology of the early 20th century. Albert Einstein introduced the cosmological constant in his general theory of relativity, describing a static universe that neither expands nor contracts. A little later, it became clear that we do not live in a static universe, but that this space with all its phenomena is highly dynamic. There is nothing that does not move in this universe. However, the physicist Alexander Friedmann came to the conclusion that Einstein's field equations also work with an expanding or contracting universe. George Lemaitre then proposed the idea of the Big Bang, in which the universe expanded from a single point. These developments led to the idea of a homogeneous and isotropic universe, which is anchored in the so-called cosmological principle. The principle states that the universe is homogeneous and isotropic on large scales, meaning that it looks the same everywhere, regardless of where you look. Let's compare this to a landscape. A homogeneous and isotropic landscape would be like a vast, endless desert in which the sand is evenly distributed everywhere and in which there are no hills, valleys, or other geographical features. No matter which direction you look or where you go, the landscape looks the same everywhere and there are no preferred or special places. In the case of the universe, this would mean that stars, galaxies, cosmic nebulae, and other phenomena are roughly evenly distributed in space. However, recent discoveries by the James Webb Space Telescope and other astronomical observations have shown that the universe may not be as homogeneous and isotropic as previously thought. The quasars and the Great Ring prove it. It may be strange to imagine the entire universe as a landscape, but on closer inspection, this idea is not so far-fetched. Only the dimensions are somewhat larger here. We have galaxies with millions or billions of stars. These wander around the universe along filaments and come together in groups. We know of gigantic empty spaces, the voids, black holes, and other phenomena. All these objects take part in the cosmic spectacle. Researchers have now discovered that one side of the sky has about 0.5% more quasars than the other side. Quasars are extremely bright galactic nuclei powered by supermassive black holes. This uneven distribution further suggests that the matter in the universe is not evenly distributed after all. The second discovery that speaks against the theory of a homogeneous and isotropic universe are two extremely large cosmic structures. The Big Ring and the Giant Arc are phenomena formed by galaxies and galaxy clusters. These structures are so large that they exceed the scale on which the universe is supposed to be homogeneous and isotropic. Basically, they are so large that our measurement techniques fail here. Such megastructures show that there are something like high mountains within the landscape of the universe, and nobody currently knows how they have emerged from or fit into the overall structure. But these are just the latest discoveries that are slowly but surely reinforcing the suspicion of a heterogeneous universe. Before these latest, exciting discoveries, there were already indications from the different expansion rates of the universe. Here, different methods of measuring the expansion rate of the universe gave different results. We know this difference as the Hubble tension. If the universe is not the same everywhere, this would explain why it is not expanding uniformly. Somewhere between the levels of the cosmic background radiation and the Cepheids, there could be a previously unknown layer of the universe, or a force that is responsible for the measurement differences, or the universe is not expanding uniformly because there is a cosmic mountain somewhere in the way. Here too, the new telescope has its part to play in current research, as scientists have used the James Webb Space Telescope to confirm the Hubble tension. Why does the cosmic background radiation show an even distribution of matter? Do you want to know a really curious fact and a fantastic theory? Let's take another look at the cosmic background radiation, or CMB for short. It does indeed show a uniform distribution of matter. The CMB is considered to be the afterglow of the Big Bang and is basically uniform microwave radiation. The radiation originated at a time around 380,000 years after the Big Bang, when the universe had cooled down enough for protons and electrons to combine to form neutral hydrogen atoms. This moment is known as recombination. Before recombination, the universe was a hot, dense plasma of ions and electrons that constantly collided with each other and scattered photons. These constant collisions ensured that the matter and radiation in the universe were tightly coupled and in thermodynamic equilibrium. During this time, radiation was strongly scattered by the dense matter, preventing it from traveling long distances without encountering particles. As the universe continued to expand and cool, temperatures eventually dropped below about 3000 Kelvin, allowing electrons to combine with protons to form neutral hydrogen. This process drastically reduced the number of free electrons, making the universe transparent to photons. Photons could finally travel unhindered, light was created, and the decoupling of matter and radiation continued. These released photons are what we see today as cosmic background radiation. It was the uniform distribution of CMB radiation that led scientists to believe that the universe was almost homogeneous and isotropic. It may have been more than 13 billion years ago when it was smaller. But now imagine, what if the universe is not expanding in an empty space, but in a space where something already is? The Big Bang and the distribution of matter shortly afterwards may have been homogeneous, but then the expanding universe encountered obstacles that disrupted the homogeneity. These obstacles can be many things, but they all lead to fantastic theories that delight space fans but give scientists a headache. The old knowledge of the Big Bang states that space only came into being with the Big Bang. The expanding universe is space. According to old theories, there is nothing outside of this space. Quantum physics has already proven that nothing cannot exist. And quantum physics has shown that a multiverse with many nested dimensions and countless universes of different shapes, sizes, and natures is more likely than the one universe in which we live. So what if our universe expands into a space in which other universes, dimensions, and previously unknown structures exist? This would of course mean that it encounters obstacles, sends other universes or dimensions away during its expansion, or they exert a resistance on our universe. An initially homogeneous Big Bang would then become inhomogeneous as a result of these encounters. Such considerations are exciting, but despite the many inconsistencies in astrophysics, they currently receive very little official attention. Is our own Earth the proof? You won't believe it, but some courageous researchers who support theories such as the multiverse have come up with an interesting comparison: our Earth. Our Earth also began as a homogeneous world. Planets in their early stages are collections of gas and dust, just like early suns are. Then they slowly develop, become more independent, take on an individual shape, wander around within the solar system, collide with other celestial bodies, and change. In the beginning, the Earth was a glowing, hot ball, and the matter was evenly distributed. Then, a heterogeneous structure developed. At least on the surface, we have large oceans and land masses that are not necessarily evenly distributed across the globe, but more randomly. The Pacific is huge, just as the Eurasian continent is very large. Africa is almost directly adjacent, while the American continents are elongated and slender. We also have more heterogeneous structures within the oceans and on the continents. Deep sea crevices and trenches, shallow sections, lagoon seas, etc. Deserts, high mountains, heavily populated areas, and sparsely populated regions have formed on the land masses. But what can we learn from this inhomogeneity in relation to the universe? Well, our Earth shows very well that the planet has changed over millions of years from a homogeneous world into a heterogeneous world, at least in part. At least the rocky planets all show traces of such changes. Mars, Venus, and Mercury also have heterogeneous structures, albeit not as extreme as on Earth. If we look at the rest of the solar system, the gas giants are homogeneous planets that have probably hardly changed their appearance for millions of years. But the diversity of our planets alone again shows the uneven distribution of matter and gas within a solar system. If we come back to the landscape of our universe, it is therefore quite conceivable that a cosmos takes on heterogeneous features in the course of its evolution, and we must come to terms with the idea that our universe is an even more dynamic entity than we previously thought. What is beyond space? The question of the boundaries of the universe extends the scientific approach to the point of merging with philosophical, even reflexive research. The spatial and temporal boundary of the universe is beyond sensory experience, and all conclusions about it, even scientific ones, are hypothetical. Modern science, however, offers several valid theories based on increasingly detailed observations of the universe. These opinions are logical conclusions based on a combination of observation and imagination. The difficult question when you think about the edge of the universe is what is on the other side. Either way, it must have existed before the Big Bang. It was the subshell from which the universe emerged, so it became part of the universe. But if the universe has no end, it can be infinite. Few scientists adapt to an infinite universe, because all kinds of disturbances of the universe can exist there. The truth probably lies somewhere in between, even if scientists do not fully understand it. Observable Universe. The word observable in this sense does not mean the ability of current technologies to detect light or other information from an object or what should be detected. It means a physical limit set by the speed of light itself. No signal can travel faster than light, so there is a maximum distance, called the particle horizon, beyond which nothing can be detected because the signals have not yet reached us. Is there anything beyond the universe? To answer the question of what is beyond the universe, we must first define exactly what we mean by universe. If you mean literally all things that can exist in space and time, then there can be nothing outside the universe. Even if you imagine the universe to be a finite size and you imagine something outside of that volume, everything outside must also be contained within the universe. Although the universe is a formless, shapeless, nameless void with absolutely nothing in it, it is still a thing and counts on the list of all things, and is therefore, by definition, part of the universe. If the universe is infinite in size, you have nothing to worry about with this puzzle. The universe, which is everything, is infinitely large and has no edges, so there is nothing to discuss from the outside. What lies beyond the edge of the observable universe? In essence, the cosmos has grown at an ever-increasing rate since its creation. Cosmologists estimate that the oldest photons we can observe have traveled a distance of 45 to 47 billion light-years since the Big Bang. This means that our observable universe is about 93 billion light-years wide, plus or minus a few light-years. These 93 billion or so light-years contain all the quarks, quasars, stars, planets, nebulae, black holes, and anything else we could possibly observe. The observable universe, however, contains only the light that has had time to reach us. The universe is disappearing. It has been nearly a century since academics first theorized that the universe is expanding and that the farther away the galaxy is from us, the faster it is receding. This is not because galaxies are physically moving away from us, but this is only because the universe exists full of gravitationally bound objects, and the fabric of space in which these objects are expands. But this picture, which has prevailed since the 1920s, has recently been modified. A mere 20 years have passed since we first understood that this expansion is accelerating and that some galaxies will move away from us at an ever-increasing rate over time. Eventually, they will most likely be unreachable, even if we could travel towards them at the speed of light. The universe thus seems to be disappearing as we age, and there is nothing humanity can do about it. What is the biggest thing in the universe? Although our sun seems huge, it looks puny compared to the biggest stars that we know. The sun is a G-type star, or a yellow dwarf, and a fairly average size on the cosmic scale. Even more massive objects are black holes, and in particular, the supermassive black holes that typically reside at the center of a galaxy. For example, the Milky Way hosts one that is about 4 million solar masses. Currently, scientists' best candidate for the largest known supercluster in the universe is the Hercules Corona Borealis Great Wall, although astronomers have spent nearly a decade debating the structure. History through space and time. The human mind is always drawn to the unknown. It's incredibly scary, but curiosity brings the will to explore beyond. Traveling through the universe is not only a journey through space, but also through time. Before we begin, let's look at some facts. To find the edge, we should first know the dimensions of the universe. Our universe is expected to be 13.772 billion years old. Pretty old, isn't it? How big is our universe really? Scientists today estimate it to be 28.5 gigaparsecs wide. To understand how big it really is, let's look at the basics of astronomical units. What's beyond space and time? It wasn't that long ago that we thought space and time were the absolute and unchanging framework of the universe. Then came Albert Einstein, who showed that different observers can disagree about the length of objects and the timing of events. His theory of relativity united space and time into one space-time. Space alone and time alone are henceforth doomed to fade into mere shadows, explained the mathematician Hermann Minkowski. Only some kind of unification of the two will preserve an independent reality. But did Einstein's revolution go far enough? Physicist Lee Smolin of the Perimeter Institute of Theoretical Physics in Waterloo, Ontario, Canada, doesn't think so. He and a trio of colleagues want to take relativity to a whole new level, and they have their sights set on space-time. They say we need to forget the home Einstein invented for us. We live inside a place called phase space. How big is the universe? By knowing the distance between your eyes and seeing the apparent displacement of your hand, we can calculate the distance to your hand. Now imagine that instead of your eyes, we have two telescopes in space, and instead of your palm, we have a very distant object. Let's say a star. We know how far apart the two telescopes are, so we can calculate the distance to the star by parallax. Thanks to Earth's orbit, which we can calculate accurately, we have just that, the ability to observe the same thing from two different points, the same telescope, moved by Earth's orbit. This approach is routinely used by astronomers to calculate the distance to celestial objects. How did the universe arise from nothing? The Big Bang Theory states that the universe arose more than 13 billion years ago from a single, unimaginably hot and dense point, also known as a singularity. It did not occur in a pre-existing space. Rather, it initiated the expansion and cooling of space itself. It explains many of the things astronomers see through ground and space-based telescopes. It's responsible for a faint glow that can be seen throughout the universe. The glow is the leftover heat from the birth of the universe, which has now cooled to just a few degrees above absolute zero. In short, it is a remarkably strong and elegant explanation of how the observable universe came into being. Conclusion. Since the first edge of the Big Bang defines the boundaries of the universe, the most distant objects humans can see are also the oldest, so it's reasonable to assume they should be about 13.8 billion miles away. But the rapidly expanding early universe was an impenetrable plasma. Also, the universe is expanding faster and faster, so light from distant objects takes longer to reach us than previously thought. Based on such considerations, astrophysicist J Group, led by Richard Goto, estimated the radius of the universe to be 45.7 billion light-years. What do you think about this exciting topic? What is beyond the cosmos? Or is there anything beyond the universe at all? Feel free to write us a comment. We're eager to hear your opinion.